Determinant of a matrix. See, what is meant by determinant of a matrix? I'll give the definition like this. Suppose if you go for a one by one, suppose the matrix contains only one element, A is equal to single element, let us say A of order 1 by 1, then its determinant A is given by notation that A is equal to, will get only single element A only. Suppose if A is a matrix of order 2 by 2, let us consider A11, A12, A21, A22. Now, determinant of A, that is det A, is given like this: A11, A12, A21, A22. That is equal to A11, A22 minus A12, A21. The element of 2 by 2 matrix. For example, 1, 2, 3, 4. I want to find determinant of this matrix. So det A is equal to 1, 2, 3, 4. We get 4 minus 6 minus 2. Now, if we go for a determinant of 3 by 3 matrix, suppose if A is 3 by 3 matrix like this with elements A11, A12, A13, A21, A22, A23, A31, A32, A33. Matrix of order 3 by 3 or 4 by 4. So to find determinant of a matrix of order 3 by 3 or 4 by 4 and so on, we'll apply this definition. So the definition is determinant of a matrix is the sum of the products of the elements of products of the elements of a any row or any column with corresponding cofactors. What I'm saying, determinant of a matrix is the sum of the products of the elements of any row or any column with corresponding cofactors. So this is the definition is applicable for 3 by 3 and 4 by 4 and so on. Suppose, what is meant by cofactors? See, I will give a definition of cofactor like this. Cofactor of any element Aij is given by minus 1 whole power I plus j into minor of Aij, minor of that element Aij. That is the definition of cofactor. Again here, cofactor involves minor. What is meant by minor? Minor of element Aij is given by, it is the det of square submatrix obtained by eliminating corresponding row and column. By eliminating corresponding row and column. It is the minor of any element definition. It is the det of square submatrix, det nothing but determinant, obtained by eliminating corresponding row and column. Now let us consider an example. A is equal to A11, A12, A13, A21, A22, A23, A31, A32, A33. Now let us consider minor of A11. So minor of A11, it is data of square submatrix obtained by eliminating first row and first column. Here our I value 1, j value 1. So it is the data of square submatrix obtained by eliminating first row and first column like this: A22, A23, A32, A33. So I can write this one as A22, A33 minus A23, A32. Minor of element A11. Similarly, if you take a minor of element A12, minor of element A12. So applying the same process, we have to eliminate here first row, second column, and finding data of remaining square submatrix. There is a A21, A23, A31, A33. That is equal to A21, A33 minus A23, A31. Similarly, minor of, let us consider minor of any element, so let us say A22, minor of A22. So this A22 is the element of second row, second column. So eliminating second row and second column, we will get data of the square submatrix A11, A13, A31, A33. That is equal to A11, A33 minus A13, A31, and so on. Like that, we can find minors of elements of a matrix. How to find cofactors? See here, I said cofactor definition is cofactor of any element. Cofactor of Aij is equal to minus 1 whole power I plus j into corresponding minor of Aij. So now let us consider cofactor of first element. Cofactor of element A11. So minus 1 whole power A11 is the element of first row and first column. Therefore I value 1, j value 1. We will get 1 plus 1 into corresponding minor of A11. So we will get here 1 into minor of A11. Already we found minor of A11. Minor of A11 is A22, A33 minus A23, A32. Similarly, cofactor of element A12, cofactor of A12. So here A12 is the element of first row, second column. So we will get minus 1 whole power I value 1, j value 2 into corresponding minor of A12. So minus 1 whole power 3, that is we will get minus 1 into minor of A12. Already we found minor of A12, that is A21, A33 minus A23, A31. Similarly, finding a cofactor of element A13, cofactor of element A13, that is equal to minus 1 whole power 1 plus 3 into minor of A13. So we will get 1 into minor of A13. Eliminating first row and third column, we will get determinant of that matrix, submatrix A21, A22, A31, A32. The determinant of the square submatrix is A21 minus A21, A32 minus A22, A31, and so on. Like that, you can find cofactors of elements. The 3 by 3 matrix. Here A11, A12, A13, A21, A22, A23, A31, A32, A33. As a definition, it is the sum of the products of elements of any row or any column with corresponding cofactors. In general, we will go for expanding that along first row. So here A11 into, I am taking first row, into capital A11 plus A12 into A12 A13 into A13. So where here A11 is a cofactor of element A11, cofactor of element A11, A12 cofactor of A12, A13 cofactor of A13. So expanding along first row, or even we can expand along second row, third row, or first column, second column, third column. Let us consider second row, A21 into A21 plus A22 into A22 plus A23 into A23 and so on. We can expand determinant of a matrix along any row or any column like this, where see here, suppose if we consider that first expression, determinant of A, that is equal to A11 plus A12 A12 plus A13 A13. So A11 into, already we found a cofactor of A11. Cofactor of A11 is, we got this value. So this is A22 A33 minus A23 A32. Now see here, next plus A12 into cofactor of A12. So cofactor of A12, see a sign of that cofactor is a negative sign. So you get here negative sign minus A12 into A21 A33 minus A23 A31 plus A13 into A13 is the cofactor of A13. Already we found cofactor of A13, that is A21 A32 minus A22 A31. So like this we can find a determinant of any matrix. Here important observation is, here we will get plus sign here, plus minus plus, plus minus plus. So similarly we can find determinant of 4 by 4, 5 by 5 also by using the same technique. One important property regarding determinant of a matrix. Suppose if you take elements of first row A11, A12, A13, multiply cofactors of second row or any other row, third row. Let us consider C into A21 plus A12 into A22 plus A13 into A23, where A21, A22, A23 are cofactors of elements of second row. So value of this expression will be definitely 0. So that is the sum of the products of elements of any row or any column with cofactors of any other row or other column is always 0. Sum of the products of elements of any row or any column with cofactors of elements of any other row or other column will be 0. Or I can take, suppose we can go for any column also. Let us consider as second column A12, A22, A32. So multiply cofactors of third column, A13 plus A22 into A23 plus A32 into A33. That will be definitely 0. So we are the elements of second column A12, A22, A32. These are cofactors of third column and so on. Like that we can say that value of that expression will be definitely 0. Properties of determinants. The first one is, for example, if you take this matrix A is equal to 1, 2, 3, 4, 5, 6, 7, 8, 0. Find determinant of this matrix. It is equal to 1 into 0 minus 48 minus 2 into 0 minus 42 plus 3 into 32 minus 35. Find the determinant of that matrix. That will go definitely 27. Check that one. We'll get 27. Now I will say the first property like this. Determinant of a matrix remains unchanged. Remains unchanged if rows and columns are interchanged. Rows and columns of a determinant are interchanged. So for example, consider this one, this matrix A. So we got A is equal to 1, 2, 3, 4, 5, 6, 7, 8, 0. Already we got determinant of that matrix, data value 27. Now I will consider, let another matrix B be like this: 1, 4, 7, 2, 5, 8, 3, 6, 0. So here the matrix B is obtained by interchanging all rows into columns or all columns into rows of a matrix A. Now if you find the determinant of this matrix, that is the det B value will be definitely 27. Using that property, determinant of a matrix remains unchanged if rows and columns of a determinant are interchanged. If any two rows or columns, of a determinant are interchanged, then the value of the determinant then the sign of the value of the determinant changes. Then the sign of the value of the determinant changes. For example, as the same example, here we have A is equal to 1, 2, 3, 4, 5, 6, 7, 8, 0. Determinant of that matrix A is 27. Now, if interchange any two rows or two columns, let us say let B matrix is obtained like this: 4, 5, 6, 1, 2, 3, 7, 8, 0. Here the matrix B is obtained by interchanging R1 and R2 of a matrix A. Then determinant of B will be definitely minus 27. Determinant of B will be minus 27. See, suppose if you go for one more interchange, we will get again one more interchange. Let us consider again interchanging, let us consider column interchange. C1 interchanging with C2. Then interchanging with C2, you will get, let us say, C matrix. C is equal to 5, 2, 8, 4, 1, 7, 6, 3, 0. Now determinant of C will be again 27, minus of minus 27 plus 27. Like this, if interchange rows and columns, determinant of a matrix takes negative sign. Suppose if you go for even number of interchanges, 2 interchanges, 4 interchanges, 6 interchanges and so on, then the sign of the value of determinant remains same. So here are two interchanges, first row interchange, next column interchange. So like that, if you go for any even number of interchanges, then the value of the determinant remains same. Suppose if you go for odd number of interchanges, one interchange, one is odd number, will get negative sign. Next 3 interchanges, 5 interchanges, 7 interchanges, like that. If you go for odd number of interchanges, then the value of the determinant, then the sign of the value of the determinant definitely changes. Now third property, if any two rows or columns, any two rows or columns of a determinant are identical, then the value of the determinant is 0. If any two rows or columns of determinant are identical, then the value of the determinant is 0. For example, A is equal to 1, 2, 3, 4, 5, 6, 1, 2, 3. So here R1 and R3 are identical. R1 is equal to R3. Therefore, I can say the determinant of that matrix A is 0 using that property. Now, fourth property, if each element of any row or any column, are multiplied by a constant k, then the value of the determinant also gets multiplied by k. If each element of any row or any column are multiplied by a constant k, then the value of the determinant also gets multiplied by k. For example, we have A is equal to 1, 2, 3, 4, 5, 6, 7, 8, 0. Taking same example, already we know that determinant of this matrix is 27. Now I will consider another matrix B like this: 2, 4, 6, 4, 5, 6, 7, 8, 0. Here the matrix B is obtained by multiplying first row of A with 2, where here that a constant k is 2 here. Multiplying first row elements of A with 2, we got a B matrix. So now if you find the determinant of B, let B value is definitely 2 into 27, that is equal to 54. The value of determinant also gets multiplied by k. Here the k value is 2. Next property, if the elements of determinant, if elements of any row or any column, are sum of two terms, then the determinant can be expressed as sum of two determinants. The elements of any row or any column of a determinant are sum of two terms, then the determinant can be expressed as sum of two determinants. For example, suppose A is equal to A1 plus X, A2 plus Y, A3 plus Z, B1, B2, B3, C1, C2, C3. Let us say the determinant of A with elements A1 plus X, A2 plus Y, A3 plus Z, and so on. Now I can express this determinant as sum of two determinants like this: A1, A2, A3, B1, B2, B3, C1, C2, C3 plus X, Y, Z, B1, B2, B3, C1, C2, C3. Expressing that determinant as sum of two determinants using that property. So this property we can extend for more than sum of two terms also. Suppose if elements of any row or any column are sum of three terms or more than three terms, then we can express that determinant as a sum of three determinants, three or more than three, like this. If the elements of any row or any column, of a determinant is added with constant multiple of corresponding elements of any other row or other column. Constant multiple of corresponding elements of any other row or other column. Other row or other column. Then the value of the determinant remains unchanged. Then the value of the determinant remains unchanged. What I am saying, if the elements of any row or any column of a determinant is added with constant multiple of corresponding elements of any other row or other column, then the value of the determinant remains unchanged. See, for example, A is equal to, let us say, A1, A2, A3, B1, B2, B3, B1, B2, B3, C1, C2, C3. Now, see here, the matrix B is obtained like this. Let us say A1 plus KA2, A2, A3, B1 plus KB2, B2, B3, C1 plus KC2, C2, C3. Now, see here, the matrix B is obtained from A by adding constant multiple of elements of corresponding elements of second column. Here I am adding a constant multiple of second column elements to first column. So now see the determinant of B. Determinant of B is given like this. See A1 plus KA2, A2, A3, B1 plus KB2, B2, B3, C1 plus KC2, C2, C3. Now, using that previous property, I can write that this determinant can be written as the sum of two determinants like this: A1, A2, A3, B1, B2, B3, C1, C2, C3 plus KA1, KA2, A2, A3, KB2, B2, B3, KC2, C2, C3. Using previous property, writing the determinant as sum of two determinants. Now, again see here, this is the determinant of A, that A, again plus, here taking K common from elements of first row. I said one property, if elements of any row or any column are multiplied by constant K, then I can write then determinant of that matrix is K times the determinant of that original matrix A2, A2, A3, B2, B2, B3, C2, C2, C3, taking element K common from the elements of first column. Now determinant of A plus K into, here see here, first column elements and second column elements are identical. In a matrix, if any two rows or two columns are identical, then value of the determinant of that matrix is 0. So we'll get into 0. So that is equal to determinant of A. Now we'll do problems on determinants. First problem. Find determinant of the matrix 0, 1, 2, 3, 1, 0, 0, 0, 2, 3, 0, 0, 3, 0, 1, 2. So the final determinant of 4 by 4 matrix. So to find determinant of any 3 by 3, 4 by 4 and so on, I said that definition. What is the definition? It is the sum of the products of the elements of any row or any column with corresponding cofactors. So we can go for any row or any column, expanding data along any row or any column. So here I will go for a second row. Why? Because second row contains 3 zeros. Whenever any row or any column contains more number of zeros, it is better to expand data of that matrix along that row or column for easier calculations. So I can write here that is equal to, let us say this is A, determinant of A, expanding along second column. So what about signs here? Signs of corresponding cofactors. So here we'll get this second row first column element, second row first column 2 plus 1, minus 1 whole power 2 plus 1 is a negative sign. We'll get negative, positive, negative, positive. So that is a minus 1 into corresponding minor. So eliminating that second row and first column, we'll get 1, 2, 3, 3, 0, 0, 0, 1, 2. Now, what about remaining? Remaining will be 0 here, plus 0 into corresponding cofactor 0. Here also 0 into corresponding cofactor, 0 into something 0. So we'll get that only the value of the determinant, that is equal to minus 1 into, again finding this 3 by 3 determinant expanding along second row for easier calculation. See here. What about signs here? We'll get negative, positive, negative. They are the corresponding signs of cofactors. So minus 1 into minus 3, corresponding minor, multiplying with the minor, eliminating second row first column, we'll get 2, 3, 1, 2. So we'll get 3 into 4 minus 3, that is equal to 3. So that is the value of the given determinant. Find determinant of these following matrices 0, 1, 2, minus 1, 0, 3, minus 2, 3, 0, and second matrix. See here this matrix is I can say that this is a skew symmetric matrix. Skew symmetric matrix. What is a skew symmetric matrix? Any matrix satisfying the condition that A transpose is equal to minus A. Any matrix satisfying the condition that A transpose is equal to minus A is called skew symmetric matrix. We have one special property here. Det of skew symmetric matrix of odd order is always 0. Det of skew symmetric matrix of odd order is always 0. What is the order of this matrix? 3 by 3. So determinant of that matrix is always 0. Let us say this is the matrix A. Determinant of A is 0. This is applicable only for 3 by 3 and so on. Suppose if you go for any 2 by 2 matrix, let us consider A is equal to 0, 1, minus 1, 0. This is also skew symmetric matrix. But what is the order here? 2 by 2. So determinant of A is equal to 0 plus 1 will get 1. Similarly, if you go for determinant of this matrix, A is equal to 0, 2, minus 2, 0 of even order, again 2 by 2. So determinant of A value is, we will get 0 plus 4, that is equal to 4. I can write this one as 4 as 2 square, here 1 as 1 square. So I can give one property here, determinant of any skew symmetric matrix of even order is a perfect square like this, 2 by 2, 2 by 2. Similarly, if you go for 4 by 4, 6 by 6 also, determinant of any skew symmetric matrix of even order is always a perfect square. But whereas determinant of skew symmetric matrix of odd order is always 0. Now, if you see that second example, find determinant of that second matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. See here, all the elements of a matrix are in consecutive order 1, 2, 3, 4, 5, 6, 7, 8, 9. If elements of a matrix are in consecutive order, the determinant of that matrix is always 0. Determinant value is always 0. So not only, see, I will give one more example. Let us consider third example. Let us say 33, 34, 35, 36, 37, 38, 39, 40. 41, 42, 43, 44, 45, 46, 47, 48. The 4 by 4 matrix, all the elements are in consecutive order, that starting with 33. So the determinant of that matrix is 0. Similarly, consider one more example 1, 2, 3, 2, 3, 4, 3, 4, 5. So here also elements are in consecutive order, but this is a second type. This is the first type of consecutive order. This is the second type. So here elements of first row is 1, 2, 3. Here the elements of second row starts with the second element of first row. Similarly, elements of third row starts with the second element of second row. This is a second type of consecutive order. Second type of consecutive order. So for this type also determinant value 0. So these are type 1, type 2. Now one important observation, suppose if you go for any 2 by 2 matrix with consecutive elements, let us consider A is equal to 1, 2, 3, 4. Determinant of A value is 4 minus 6 minus 2 not equal to 0. So this property holds good only for matrices of order 3 by 3 and more, not applicable for 2 by 2 matrices. How to find determinant of these matrices? 5, 2, 2, 2, 5, 2, 2, 2, 5. And second one 1, 0, 0, 5, 0, 1, 5, 0, 0, 5, 1, 0, 5, 0, 0, 1. Consider the first matrix here. So for this type I will give one shortcut method. Whenever elements of the given matrix are like this x, a, x, a, x, then the value of the determinant of that matrix will be x minus a whole square into x plus 2a. So here the principal diagonal elements are equal to same element x and other elements are equal to same element a. In that case we can apply the shortcut formula x minus a whole square plus x plus 2a. So here also the principal diagonal elements equal to same number 5 and other elements are equal to same number 2. So I can apply this formula x minus a means 5 minus 2 whole square into 5 plus 2a. Here our a value is 2. 2 into 2 4. So we will get 5 minus 2 whole square, that is 3 square is 9. 9 into 9, that is equal to, you will get 81. Applying that shortcut formula. Similarly, to evaluate this determinant of this matrix, we have one more shortcut formula. We have 100k, 01k0, 0k10, k001. If elements of the matrix are like this, I can apply this formula, shortcut formula 1 minus k square whole power order by 2. 1 minus k square whole power order by 2. So here, see the elements of the matrix, see principal diagonal elements must be equal to 1 and other diagonal elements equal to same number k and remaining elements must be 0. So to apply the shortcut formula, the conditions are, the first condition is principal diagonal elements must be equal to 1, other diagonal elements equal to same number k and all remaining elements must be equal to 0 and order of that matrix must be even order. Order must be even order. Now see here, principal diagonal elements equal to unity, other diagonal elements equal to same number 5 and all remaining elements are zeros and order of that matrix is even order. So in that case I can apply that shortcut formula 1 minus k square. 1 minus k square means here our k value is 5. 1 minus 5 square whole power order by 2, 4 by 2. So we will get minus 24 whole square, that is equal to 576. will get. Next problem. Given the determinant of the matrix 130, 264, minus 102 is minus 12, then the determinant of the matrix 260, 412, 8, minus 204 is. See, to find determinant of this matrix, it is a 260, 412, 8, minus 204. I will apply properties of determinants. Using properties of determinants, I can take see a 2 common from first row elements. 2. I can write here 130. Again taking 2 common from second row elements into 2. Take 2 outside. We will get 264. Again taking 2 common from third row elements. We will get into 2 again. We get minus 102. Using properties of determinants, we can take common factor from elements of any row or any column from a given determinant. So we will get 2 into 2 into 2, 8 into, it is given that determinant of that matrix 130, 264, minus 102 is minus 12. So we will get minus 96. So we need to find determinant of this matrix. Using properties of determinants, I can write 8 into minus 12, that is equal to 96. Next problem. If A is a square matrix of order 3 with determinant 2, then the value of determinant of 4 into A power minus 5 is. Here also we have to go for a properties and determinants. So we have these properties, determinant of Ka, where K is any constant, it is equal to K power n into determinant of A, where A is a matrix of order n by n. Similarly, we have det of A power n is equal to det A power n. Det of A power n is equal to det A power n. So where here n belongs to set of integers. Here for a special case, let us say for n is equal to minus 2, I can write det of A power minus 2 is equal to det A power minus 2, that is equal to, I can write 1 by det A whole square. So we have to use these properties. Now find determinant of that matrix. Given that det A value 2, we need to find det of 4 into A power minus 5. 4 into A power minus 5, that is equal to, applying first property, det of Ka is equal to K power into det A, we will get 4 power, given that A is a matrix of order 3, we will get 4 cube into determinant of A power minus 5, that is equal to 64 into, again applying this property, det of A power n is equal to det A power n, where n belongs to set of integers. So I can write det A power minus 5, that is equal to 64 into, here det A value is given as 2, so 2 power minus 5, so we will get 64 by 32, that is equal to 2. So for this problem 2 is the correct answer. Next problem is a gate 13 question. Which one of the following does not equal to determinant of this matrix? So 1x x square, 1y z y square, 1z z square. So given A, B, C, D options are there. Now we will verify one by one. First option A. See here, that is the given matrix. Let us say this is A. A is equal to that determinant of that matrix. Now let us consider, I said one property. If elements of any row or any column are added with the constant multiple of any other row or other column, then the value of the determinant is unchanged. What I am saying? If elements of any row or any column are added with the constant multiple of corresponding elements of any other row or other column, then the value of determinant remains unchanged. Now that is, I can say that Ri implies Ri plus Krj, or corresponding column operation Ci implies Ci plus Kcj. So mathematically I can write like this. If elements of any row or any column are added with constant multiple of corresponding elements of any other row or other column, then that value of determinant does not change. So if you apply these type of operations, determinant of A does not change. Determinant of A value does not change. Now, so applying this property to the given problem, by here C2 implies C2 plus C1, C3 implies C3 plus C2. So here comparing that what I said Ci implies Ci plus KCj. This operation does not change value of the determinant. So here I value 2, K value 1, J value 1. Here also I value 3, J value 2 and whereas K value 1. So applying these operations we will get, I can write value determinant never changes. That A is equal to, I can write 1 x plus 1 here C3 plus C2 in place of C3 plus C2 x square plus x square plus x means taking x common at x into x plus 1 here y plus 1 y square plus y means taking y common y into y plus 1 z plus 1 z into z plus 1. So these two determinants are same, that A is equal to, these two are same, but you will see that option A, see here by interchanging second column and third column we will get option A. Interchanging second column and third column we will get option A. So if you go for interchange of any two rows or two columns, then the sign of the value of determinant changes. So here value of the determinant is that is equal to, I can write minus det A. Both are not equal. So determinant of this matrix is minus det A because interchanging any two rows or two columns, the value, the sign of the determinant changes. But whereas option B, check option B. So which one of the following does not equal to, means both are not equal. This one is equal to minus of det A. So option A is correct. So verifying option B, C, D. If option A is correct, option B, C, D are wrong. So see here, what about option B? Elements of here first row will be 1 x plus 1 x square plus 1. Now here applying C2 implies C2 plus C1, C3 implies C3 plus C1 on A. Applying C2 implies C2 plus C1, C3 implies C3 plus C1. We will get this matrix. So if you go for these type of operations, the determinant of that matrix never changes. Therefore, both are equivalent. But we have to find out which one of the following does not equal to. So this is not the correct option. Both are equivalent. Similarly, you see the option C. So applying here, in place of R1, replacing R1 minus R2. Replacing R1 minus R2. Here, for option C, R1 implies R1 minus R2, R2 implies R2 minus R3. We will get option C. So in this case also determinant of A and determinant of this matrix both are equivalent, no change. So this is also not correct option. Similarly option D. So for option D, you have to go for let us consider here applying R1 implies R1 plus R2 and R2 implies R2 plus R3. Applying these operations on this given matrix, you will get option D. So here also determinant of the given matrix and determinant of this matrix both are equivalent. So this is also not correct option. So because the given question is which one of the following does not equal to, means these two are not equal because this is equal to minus of det A. So that is option A only correct, B, C, D are not correct using properties of determinants. Next topic, rank of a matrix. I will give definition, rank of a matrix. Rank is the highest order non-zero determinant of given matrix. Non-zero determinant of given matrix. Rank is the highest order non-zero determinant of given matrix. For example, A is equal to 1, 2, 3, 4, 5, 6. This is a matrix of order 2 by 3. So we can't find data of this matrix because this is not a square matrix. So we have to go for the highest order determinant. Here we can form the highest order determinant of order 2 by 2. The highest possible det is of order 2 by 2. So consider any 2 by 2 det by eliminating any column. Let us eliminate the first column. So 2, 3, 5, 6. Det of this matrix is 12 minus 15 minus 3 not equal to 0. So whenever det value non-zero, then order of that given matrix will give the corresponding rank. So it implies rank of this matrix is 2. What I am doing, given matrix is of order 2 by 3. So the highest possible det is of order 2 by 2 because we can find only det of square matrix only. So by eliminating any column, not only first column, we can go for even second column also. Eliminating only second column, we will get 1, 4, 3, 6. So 6 minus 12 minus 6 not equal to 0. So if at least one det is non-zero of 2 by 2, then I can say that det rank of that matrix is 2. Similarly, if you go for another example, A is equal to 1, 2, 3, 4, 5, 6, 7, 8, 0. I want to find rank of this matrix. Is of order 3 by 3. So find determinant of this matrix. We can find determinant of this matrix directly because this is a 3 by 3 matrix. So the highest possible det is of order 3 by 3. Finding determinant of this matrix, it will give 27. Already we did this problem previously. So 27 not equal to 0. So determinant not equal to 0 of order 3 by 3. Therefore it implies rank of this matrix is 3. Similarly, if we consider another example, example 3, A is equal to 1, 2, 3, A is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. I want to find rank of this matrix. Rank of this matrix. See, it is a matrix of order 3 by 3. Finding determinant of this matrix, det A value. Det A value is 0 because already we know that if elements of a matrix are in consecutive order, determinant value is 0. If determinant value is 0, then I can't say that rank cannot be 3. Rank cannot be 3. I can say that rank of that matrix less than 3 in that case. Since determinant of 3 by 3 is 0, rank less than 3. So in that case, you have to go for next lower order. Next lower order. Consider any 2 by 2 submatrix by eliminating any row and any column. By eliminating, so let us consider this eliminating third row and third column. We will get 1 2 by 2 submatrix. Find that of that submatrix, that will give 5 minus 8, that is equal to minus 3 not equal to 0. Finding that of next lower order submatrix by eliminating third row, third column. We can eliminate any row and any column to form 2 by 2 det. So this is not equal to 0. So order of this 2 by 2 det is 2. Therefore rank of this matrix is 2. Rank of this matrix is 2. Now taking another example, example 4, let us consider this matrix. A is equal to 1, 2, 3, 2, 4, 6, 3, 6, 9. I want to find rank of this matrix of order 3 by 3. So to find rank, first find det of that matrix, det value. So here det value will get 0. Why? Because see here det A value using properties of determinants. I can take here, let us consider from second row elements take 2 common. So I can write 2 into 1, 2, 3, 1, 2, 3, 3, 6, 9. Using properties of determinants, taking 2 common from second row elements, we will get 2 into this one. Here, first row and second row are identical. We know that in a matrix, if any 2 rows or 2 columns are identical, that value is 0. So 2 into 0, that is equal to 0. So that value is 0. So not only 2 here, even we can take 3 common from third row elements. If you take 3 common, then we will get 1, 2, 3 again. So in that case also we get all rows are identical 1, 2, 3, 1, 2, 3, 1, 2, 3. So we get determinant value, that value 0. Now so I can say that here rank of that matrix, rank of A not equal to 3, since that value 0. So rank not equal to 3, I can confirm that rank of that matrix, rank of A must be less than 3. Must be less than 3. Now consider next lower order submatrix taking any 2 by 2, data of any 2 by 2 submatrix by eliminating, let us consider eliminate first row, first column, we will get 4, 6, 6, 9. Finding data of any lower order 2 by 2 matrix. It is a 2 by 2. So 36 minus 36 will get 0. Or eliminate second row, second column, will get 1, 3, 3, 9. That is another lower order, data of lower order submatrix of 2 by 2. So 9 minus 9 again 0. So like this, for this matrix, all 2 by 2 debts will be 0. I can confirm that all 2 by 2 debts 0. All 2 by 2 debts 0. If at least one 2 by 2 debt not equal to 0, I can confirm that rank is equal to. But here all 2 by 2 debts are 0. In that case, we have to go for next lower order. Next lower order is 1 by 1. So since it is a non-zero matrix, so take any 1 by 1 debt here by eliminating second row, third row, and second column, third column, you will get only single element 1. So det A value single element 1, that is det of single element is again itself not equal to 0. Therefore I can confirm that rank of that matrix is 1, because this is a 1 by 1 det. It implies I can confirm that rank is equal to 1. So here I can confirm I can give one property. Rank of any non-zero matrix is always greater than or equal to 1. Only rank of null matrix is 0. Only rank of null matrix is 0. So finally we got rank of this matrix is 1. Now I will give properties of rank of a matrix. Properties of rank of a matrix. First property. So I can write rank of A, I can denote it by rank of A is equal to row of A. That is the notation. First property, rank of A of order m by n is always less than or equal to minimum of m comma n. Minimum of m comma n. Similarly, rank of AB always less than or equal to minimum of rank of A, rank of B. Next, rank of AB greater than or equal to rank of A plus rank of B minus n, where A and B are matrices of order n by n. Rank of AB is always greater than or equal to rank of A plus rank of B minus n, where A and B are matrices of order n by n. Next, rank of A plus B less than or equal to rank of A plus rank of B. Next, rank of A minus B is always greater than or equal to rank of A minus rank of B. Rank of A minus rank of B. Next, can give maximum of 0 rank of A plus rank of B minus n less than or equal to rank of AB less than or equal to minimum of rank of A rank of B. So we have to consider maximum of these two things, 0 or rank of A plus rank of B minus n. So where A and B are matrices of order n by n. A and B are matrices of order n by n. Now, next property, modulus of rank of A minus rank of B always less than or equal to rank of A plus B less than or equal to rank of minimum of rank of A plus rank of B comma m comma n, where A and B are matrices of order m by n, where A and B are matrices of order m by n. Similarly, you can say that the rank of null matrix is always 0. I said that this one, rank of null matrix is 0. Next, rank of non-zero matrix, rank of any non-zero matrix is always greater than or equal to 1. Always greater than or equal to 1. Next property, rank of a non-singular matrix of order n by n is n. Why? See here, it is a non-singular matrix. Non-singular matrix means always determinant of that matrix not equal to 0. So determinant of a matrix is not equal to 0, then rank is equal to order of that matrix. So it is given that A is a n by n matrix, therefore rank is equal to n. Next property, rank of a singular matrix of order n by n is always less than n. Rank of a singular matrix of order n by n is always less than n, because see here given matrix is singular matrix. Singular matrix means determinant value 0. Determinant value 0. Whenever determinant value is 0, then rank cannot be 3. Sorry, rank not equal to n, because A is a matrix of order n by n. You have to go for next lower order. So definitely rank cannot be n, because determinant value is 0. Next property, if rank of a matrix of order n by n is n, then rank of adjoint A is also n. Similarly, if rank of a matrix of order n by n is equal to n minus 1, then in that case rank of adjoint A is 1. Similarly, rank of A of order n by n less than or equal to n minus 2. In that case, then rank of adjoint A is 0. So, there are some important properties of rank of a matrix. Next, finding rank of a matrix using echelon form. Matrix using echelon form. Finding rank of a matrix using echelon form. So now here what is meant by echelon form of a matrix? First, echelon form of a matrix. Now consider an example. A is equal to 1 2 3 0 4 5 0 0 6 0 0 6. Now here I can say that rank of this matrix, echelon form, which is in echelon form. I will tell the conditions of echelon form. Next, number 2, B matrix. Consider B matrix like this: 1 minus 1 0 0 0 0 1 minus 1 0 0 0 5 0 0 0 0 0 0 0 0. Here also I can say that this matrix is in echelon form. This matrix is in echelon form. Consider another example 3. Let us consider C matrix. C is equal to 1 0 0 0 0 1 0 0 0 0 0 1 0 0 1 0 0 0 0 0. This matrix is not in echelon form. So now I will tell the conditions of echelon form. A matrix is said to be in echelon form if number of zeros before the first non-zero element in each row increases with row number. What I am saying, first condition is the number of zeros before the first non-zero element in each row increases with row number. See here, first row, this is the first non-zero element, before that one no zeros. Second row, this is the first non-zero element, before that one there is only one zero. So rows, number of zeros are increasing. Row number 1 no zeros, row number 2 only 1 0. Now if you see the third row, this is the first non-zero element, before that one 2 zeros are there. So here 1 0, 2 zeros, no zeros. So zeros are increasing from top to bottom with row number. That is the first condition. Number of zeros before the first non-zero element in each row increases with row number. The second condition is if there are any zero rows, they must be below the all non-zero rows. If there are any zero rows, they must be below the all non-zero rows. Here this matrix does not contain zero rows, so no need to apply that second condition. Second condition is optional. Suppose if you take second matrix here, B matrix, 1 minus 1 0 0. So here see that check that first condition. What is the first condition? Number of zeros before the first non-zero element in each row increases with row number. See the first row, this is the first non-zero element, before that one no zeros. Second row, this is the first non-zero element, before that one there are 2 zeros are there. Here no zeros, 2 zeros, zeros are increasing. In third row, this is the first non-zero element, before that one 3 zeros are there, more than 2. So with row number of zeros also increases. Row number 1 no zeros, row number 2 2 zeros before the first non-zero element, row number 3 3 zeros before the first non-zero element. So here one important observation. So don't count these zeros. You have to count zeros only. You have to count zeros only before the first non-zero element. Before the first non-zero element. So first condition satisfied. What about second condition? I said if there are any zero rows, they must be below the all non-zero rows. See here, the fourth row and fifth row are completely zero rows lying below the all non-zero rows. That condition is not applicable for first matrix because there are no zero rows here. So here the matrix B satisfying both the conditions, first condition, second condition. Therefore, which is in echelon form. Which is in echelon form. Now consider that matrix C here. I am saying that this matrix is not in echelon form. See, if you take first row, this is the first non-zero element. Before that one no zeros. We should not count these zeros. These are useless. Don't count these zeros. You have to count zeros only before the first non-zero element. So no zeros here. Here only 1 0. Don't count these zeros. You have to count zeros only before the first non-zero element, only 1 0. Here 3 zeros more than 1. Okay, now see here only 2 zeros before the first non-zero element. So not satisfying that first condition. Number of zeros before the first non-zero element in each row increases with row number. Row number 2 only 1 0. Row number 3 3 zeros. But whereas row number 4 contains 2 zeros less than 3. So zeros are not increasing from top to bottom. So which is not in echelon form. But we can convert this matrix into echelon form by applying this operation. That is interchanging R3 and R4. Interchanging R3 and R4. I can write that matrix like this: 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0. Now which is in echelon form, satisfying both the conditions of echelon form. First condition, zeros are increasing before the first non-zero element in each row, and second condition, this is a completely zero row lying below the all non-zero rows. There is a completely zero row lying below the all non-zero rows. So which is in echelon form. So what is the advantage of echelon form? Using echelon form, we can find rank of the given matrix. That is the advantage of echelon form. So here in this matrix, so I can give formula like this: rank in echelon form. That is the advantage of echelon form. Rank in echelon form is given by number of non-zero rows. Number of non-zero rows. So if you take the first matrix, so here which is in echelon form, so rank in echelon form is equal to here 1 2 3, all 3 rows are non-zero rows, therefore here rank is equal to 3. For this matrix, rank is equal to 3. For the second matrix, here also count number of non-zero rows. First 1 2 3, here also 3 zeros are non-zeros, a fourth row and fifth row are completely zero rows. So for this matrix also rank is equal to 3. I can say that rank is equal to 3. See that third matrix C, here count number of non-zero rows. Here first row non-zero, second row non-zero, third row non-zero, fourth row also non-zero, but whereas fifth row is completely zero row. So number of non-zero rows are 4, therefore I can say that rank is equal to 4. So this is the advantage of echelon form. So by using echelon form we can find rank of the given matrix. We have two methods to find rank of a matrix. First one, determinant method. Second one, echelon form method. Echelon form method. So whenever given matrix is of order 2 by 2, 2 by 2, 3 by 3, it is better to go for a determinant method. We can find we can apply very easily the determinant method to find rank of that matrix. So whenever given matrix is of order 3 by 4, 4 by 4, 5 by 5 or any higher order. So all these are higher order matrices more than 3 by 3. So whenever given matrix is of higher order, it is better to apply echelon form method. Echelon form method. Now we will see one example. Let us consider the matrix A is equal to 6044 minus 2 14 8 18 14 minus 14 0 minus 10. We have to find the rank of this matrix. Find rank of here. Suppose if you go for that first method, det method, see here what is the order of this matrix is a 3 by 4. Suppose if you want to apply det method, what is the highest possible det is of order 3 by 3. So like this, how many 3 by 3 dets are available here? See here, if you remove that first column, you will get one 3 by 3 det. If you remove that second column, you will get one 3 by 3 det. Removing that third column, one 3 by 3 det. Removing fourth column, one 3 by 3 det. So like this, there are 4 3 by 3 dets are available. 4 3 by 3 dets are available. So we need to check all those 4 3 by 3 dets. Suppose if at least one 3 by 3 det is not equal to 0, I can confirm that rank is equal to 3. Suppose if all 4 3 by 3 dates are 0, in that case rank of that matrix cannot be 3. In that case we have to go for next lower order, that is a 2 by 2 matrix. So it is somewhat difficult to find rank of this matrix using that method. So in this case it is better to go for echelon form of a matrix. Rank of this matrix using echelon form. See here, reducing A into echelon form. A into echelon form. So you have to get that reducing A into echelon form. So I will apply these operations. R2 implies 3R2 plus R1, so that we can make this element 0. Next R3 implies 6R3 minus 14R1. So by applying these operations, that matrix will be reduced to 6 0 4 4 0 42 28 58 0 minus 84 minus 56 minus 116. Applying these operations, that matrix will be reduced to like this. Now which is not in echelon form. To get echelon form, we have to make this element also 0. So applying this operation, so in place of R3, replace R3 with R3 plus 2R2, so that we can make this element 0. R3 plus 2R2. So that applying that operation 6044, we get 0 42 28 58 0 0 0 0. Applying that operation R3 plus 2R2. Now which is in echelon form? So we know that rank in echelon form is given by number of non-zero rows. So here first row and second row are non-zero, but whereas that third row is completely 0 row. So I can say that rank is equal to 2, because number of non-zero rows are 2. So like this you can find a rank of a matrix using echelon form method. Consider one gate problem regarding the rank. See, this is given in gate 14. Two matrices A and B are given below. A is equal to PQRS, B is that one. If the rank of the matrix A is n, then the rank of the matrix B is given option A, B, C, D. So given rank of A is n, we need to find rank of matrix B. See here, we can do this problem like this. First find determinant of that matrix, det of that matrix. Det A is equal to PS minus QR. PS minus QR. Next finding det B. So finding det B value, P square plus Q square into R square plus S square minus PR plus QS into PR plus QS is a PR plus QS whole square. PR plus QS whole square. So that is equal to P square R square plus P square S square Q square R square plus Q square S square. Expanding this one using A plus B whole square, we will get P square R square minus Q square S square minus 2 PR QS. Now P square R square, P square minus P square R square, Q square S square minus Q square S square will get cancelled. Now we can add that remaining 3 terms like this, PS minus QR whole square. See here, combining these 3, I can write PS minus QR whole square. Now see here, determinant of A is PS minus QR, det B is a PS minus QR whole square. Suppose if PS minus QR value not equal to 0, det A value not equal to 0. If det A value not equal to 0, rank is equal to order of that matrix. What is the order of A? Order of A is 2. So in that case, rank of A is 2. Rank of A is 2. If PS minus Q are not equal to 0. If PS minus Q are not equal to 0, PS minus QR whole square also not equal to 0. So in that case also I can say that PS minus QR not equal to 0 whole square also. In that case I can say that rank of B also 2. Rank of B 2. Here PS minus QR not equal to 0. I can say that rank of A is 2. So here rank of B follows rank of A because it depends upon that PS minus QR value. PS minus QR value. Similarly, suppose another case, if PS minus QR value is equal to 0, if PS minus QR value is equal to 0, in that case I can say that rank of A is less than 2. In that case rank of A less than 2. If PS minus QR is equal to 0, then PS minus QR whole square also is equal to 0. This value. If this is 0, this is also 0. In that case, I can say that rank of B is also less than 2. Rank of B is also less than 2. Similarly, if suppose all P is equal to Q is equal to R is equal to S is equal to 0, all elements of A are 0. In that case, I can say that rank of A is 0 because that will become null matrix A. PQRS is equal to 0. So if PQRS is equal to 0, then P square plus Q square elements of B also will become 0. B also will get null matrix 0 0 0 0. Applying this condition PQRS is equal to 0, then elements of B also 0. So in that case I can say that rank of B is also 0. Since rank of null matrix is 0. See, if first case PS minus QR not equal to 0, rank of A 2, PS minus QR whole square also not equal to 0, rank of B also 2. So rank of A here, finally I can say that rank of B is following rank of A. Rank of B is following rank of A. Here also this is rank of A less than 2, rank of B also less than 2. Rank of A 0, rank of B 0. So in every case rank of B is following rank of A. Therefore it is given that rank of A is n, then definitely rank of B also n. So that is option C is correct. So now we can do the same problem by applying shortcut method also. That is we have rank of A into A transpose is equal to rank of A. So here given A is a PQRS, and what about A transpose? A transpose is a PRQS. A transpose is PRQS. Now multiplying A into A transpose, that is equal to PQRS into PRQS. Multiplying these two, it will give P square plus Q square, PR plus QS, R square plus S square. The multiplication of A into A transpose. So now here see that A into A transpose is giving B. See here B, both are equal here. So that is equal to B. So we know that rank of A into A transpose is equal to rank of A. So here A into A transpose is B. So therefore I can say that rank of B is equal to, in this case, rank of A. Rank of B is equal to rank of A. Given that rank of A is n, therefore I can say that rank of B is also n. Next problem on rank. Let A is equal to A is A, where given that 1 less than equal to I comma j less than equal to n is defined by A is A is equal to I into j. A is I into j for all I comma j with n greater than equal to 3, the rank of the matrix A is. So to find rank of A, here let us consider, let n is equal to 3. Then what about elements of A? Elements of A will be here A11, A12, A13, A21, A22, A23, A31, A32, A33. So apply that condition, elements of that matrix A satisfying the condition that Aij is equal to I into J, where I represents corresponding row number, corresponding column number. Here I value 1, J value 1 for the first element. So 1 into 1, 1. For the second element I into J, 1 into 2, 2. For the third element 1 into 3, 3. This element 2 into 1, 2. 2 into 2, 4. 2 into 3, 6. So like that we'll get 3, 6, 9. Applying that condition 3, 6, 9. Now see here to find rank of this matrix. To find rank of this matrix, see I will find det A value. Det A value. So det A 1, 2, 3, 2, 4, 6, 3, 6, 9. So determinant of this matrix is 0. How can you say determinant of that matrix is 0? Suppose if you take element 2 common from second row elements, it will be 2 into 1, 2, 3, 1, 2, 3, here 3, 6, 9. 3, 6, 9. So here first row and second row are identical. Therefore, determinant value 0. So if determinant value 0, rank of that matrix cannot be 3. It must be less than 3. So in that case, we have to go for next lower order. What is the next lower order here? Next lower order is 2 by 2. Consider any 2 by 2 matrix. Consider any 2 by 2 matrix by eliminating one row and one column. So let us consider this. So 1, 2, 2, 4. So we'll get 4 minus 4, 0. So like this, all 2 by 2 debts will be 0. All next lower order 2 by 2 debts will be 0. So therefore, I can confirm that rank of A cannot be 2 because debt value 0. Rank of A cannot be 2. So we have to go for next lower order. Next lower order is 1 by 1 only. So since it is a non-zero matrix, so definitely rank of that matrix is at least 1. So I can say that rank of this matrix is 1 in this case because 3 by 3 debt 0, all 2 by 2 debt 0, but only 1 by 1 debt not equal to 0. 1 by 1 debt not equal to 0, therefore rank is equal to 1. So rank of this matrix is 1. Option B. That is using det method. Now we can do the same problem like this also by applying echelon form method. By applying echelon form method. So here this is a matrix A 1, 2, 3, 2, 4, 6, 3, 6, 9. Now apply these operations. R2 implies R2 minus 2R1. R3 implies R3 minus 3R1. So that matrix A will be reduced to A is equal to, I can write 1, 2, 3. R2 minus 2R1 will get 0, 0, 0. R3 minus 3R1 will get again 0, 0, 0. So which is in echelon form? Which is in echelon form? So therefore, rank in echelon form is equal to number of non-zero rows. There is only one non-zero row, that is the first row. Therefore, rank is equal to 1. That is the second method to find rank of that matrix. Next problem on rank. If A is equal to Aij is defined by Aij is equal to I plus j for all I comma j where I and j greater than or equal to 3. In that case, what is the rank of matrix A? So in that case only, same like previous problem, better to take example here, at least value of I 3, least value of j 3. So let consider a matrix A of order 3 by 3 is equal to elements of that matrix A will be A11, A12, A13, A21, A22, A23, A31, A32, A33. So now apply that condition, elements of that matrix satisfying condition Aij is equal to I plus j. So apply that condition here, I value 1 for the first element, j value 1. So 1 plus 1, 2, 1 plus 2, 3, 1 plus 3, 4. Next we will get 3, 4, 5, 4, 5, 6, 4, 5, 6. Now finding rank of that matrix. So finding rank of this matrix, so we can do in two ways. We can go for det method or echelon form method. Suppose if you go for echelon form method, R2, replacing R2 with 2R2 minus 3R1 and replacing R3 with 2R3 minus 4R1. R2 with 2R2 minus 3R1, R3 with 2R3 minus 4R1. So that if you apply these operations, that matrix will be reduced to 2, 3, 4. You will get 0 here, 2R2. Here you will get 8 minus 9. You will get minus 1. 2R2, 10 minus, you will get 12 minus 2. R3, 2R3 minus 4R1, you will get this element 8 minus 8, 0. 2R3, 10 minus 12, you will get minus 2. Here 12 minus 16, you will get minus 4. So here to get echelon form, we have to make this element into 0 by applying this operation. Applying R3 implies R3 plus 2R2, so that we can make this element into 0. R3 implies R3 plus 2R2. So then that matrix will be reduced to 2, 3, 4. First row same, second row also same, third row 0, 0, R3 plus 2R2. So we will get R3 plus 2R2. So minus 4. You will get here also minus 4 plus 2 into minus 2 will get minus 4 plus minus 4 will get minus 8. Next problem on rank. A is equal to A is A, defined by A is equal to I plus J for all I comma J, where I greater than or equal to J 3, J greater than or equal to 3. Let us find out rank of this matrix. Let us consider least value of I 3, least value of J 3. So consider A of order 3 by 3. So then elements of that matrix will be A11, A12, A13 like this. Now apply that condition. What is the given condition? Aij is equal to I plus J. So here for the first element I is 1, J is 1. So we get 1 plus 1, 2. 1 plus 2, 3. 1 plus 3, 4. So like that we will get remaining elements. Now reducing that matrix into echelon form by applying these operations. First applying these operations, we have to make these two elements into zeros. R2 minus R2 implies 2R2 minus 3R1, R3 implies 2R3 minus 4R1. That will give first row same here 2, 3, 4. Second row and third row 0 minus 1 minus 2, 0 minus 2 minus 4. Again to get the echelon form, we have to make this element into 0 by applying this operation. R3 implies R3 minus 2R2. So then we will get 2, 3, 4, first row same, second row same, third row we will get 0, 0, 0, which is in echelon form. Which is in echelon form. Which is in echelon form. We know that rank in echelon form is given by number of non-zero rows. So here number of non-zero rows are only 2. Therefore, rank of this matrix is 2. Next problem on rank. If A and B are square matrices of order 6 by 6 with rank of A 3, rank of B 4, then the range of rank of AB and rank of A plus B. So to find range of rank of AB and A plus B, we have direct formulas. Already I have given in properties. Rank maximum of 0 comma rank of A plus rank of B minus n less than or equal to rank of AB less than or equal to minimum of rank of A, rank of B. So to find range of rank of A into B, we can apply this formula. So here it implies maximum of 0 comma rank of A, given rank of A 3, rank of B 4 minus n, where n is the order of A and B. Here A and B should be of same order. So n is 6 less than or equal to rank of A into B less than or equal to minimum of rank of A, rank of B. Rank of A 3, rank of B 4. Applying this formula. So it implies maximum of 0, 4 plus 3 7, 7 minus 6 1 less than or equal to rank of AB less than or equal to minimum of 3, 4 is 3. So maximum of 0, 1 is 1. So I can write 1 less than or equal to rank of AB less than or equal to 3. This is the range of rank of A into B. Similarly, we can find range of rank of A plus B also by applying this formula. We have modulus of rank of A minus rank of B always less than or equal to rank of A plus B less than or equal to minimum of rank of A plus rank of B comma m comma n, where A and B are matrices of order m by n. Now applying this formula here, rank of A is 3, rank of B 4, modulus less than or equal to rank of A plus B less than or equal to minimum of rank of A plus rank of B. So rank of A plus rank of B is 3 plus 4, this is 7, m comma n. So here m comma n are number of rows and number of columns in A and B. Here A and B, where A and B are matrices of order, same order m by n. So here given matrix A and B are of order 6 by 6. So you will get m6, n also 6. So you get 3 minus 4 minus 1, modulus of minus 1 is 1, less than or equal to rank of A plus B, less than or equal to minimum of 7 comma 6 comma 6 is 6. So the range of rank of A plus B is 1 less than or equal to rank of A plus B less than or equal to 6. Next problem on rank. If A is a square matrix of order 6 such that A square is equal to 0, if 0 means that is a null matrix, then rank of A is given option A, B, C, D. So to solve this question, we have to apply this formula given one property of rank of a matrix, that is a rank of AB, the rank of product of two matrices always greater than or equal to rank of A plus rank of B minus n, where A and B are matrices of order n by n. A and B are matrices of order n by n. Then rank of product of two matrices A and B, that is A into B, greater than or equal to rank of A plus rank of B minus n, applying this property. So I can write from this one, I can write rank of A plus rank of B minus n less than or equal to rank of AB. Same thing. Here in this inequality, put A is equal to B. Put A is equal to B in this inequality. We will get rank of A plus rank of A minus n less than or equal to rank of A square. Rank of A square. Now, so here rank of A plus rank of A is 2 rank of A. 2 rank of A minus n in that given matrix, where n is the order of A and B. It is given that it is a square matrix of order 6, so that n value is 6 here, less than or equal to rank of A square. It is given that A square is a null matrix, so rank, we know that rank of null matrix is always 0, so rank of A square is 0. So I can write this one as 2 rank of A less than or equal to 6. 2 rank of A less than or equal to 6. It implies rank of A less than or equal to 6 by 2. It implies rank of A less than or equal to 3. Rank of A less than or equal to 3. So therefore that is the option A is correct. Here to apply this shortcut formula, to apply this formula here should not get fraction value. You should get only integer value. So suppose if you get any value like this, suppose if we get 5 by 2 on RHS, 5 by 2 on RHS, You have to take here 5 by 2 is 2.5. So 2.5 means in that case I can take rank of A less than or equal to 2. Should take only integer part of this value. Integer part of this value. So 5 by 2 integer part is 2.